This meeting is being recorded.
Okay, dear colleagues, the talk today is presented by Professor Valentin Iliev from our institute on an aspect of second quantum revolution. Please.
Quantum revolution. Yes. Okay. First, I would like to make a personal remark. I'm a mathematician, not a physicist. And the language of physics is almost foreign language for me. That's why please forgive me if I make some naive mistakes. And moreover, I cannot, I don't know well the terminology in Bulgarian. That's why I make, in any case, I'll make it in English, following the presentation, of course. Moreover, I would like to apologize that I'm not using Dirac notation because the audience here consists of mathematicians. Almost all are mathematicians, so they do not like Dirac notation. I don't like it too. I think that it is cumbersome and okay, I'll use a standard notation. Let's begin. This is the short abstract of the talk. It is devoted to the experiment made by one of the Nobel Prize laureates in physics from...
Can you make full screen?
Sorry?
Full screen, if you possible.
Full screen.
Yes.
Okay, but I have to... This is the most wide. I don't know where to
Control L, and then it will become full screen.
Control L.
Yes.
Nothing happens.
But
Okay.
maybe I can interfere from my screen, which is not big. It looks very good.
So you cannot see the...
It's okay.
The presentation. So what's the problem?
According to me, there is no problem. And sometimes actually this view, it's full screen, not presentation. Full screen gives access to various menus and buttons. Otherwise, I think the size of the presentation and the letters is the same. But yes.
So I'll make
yes, now
something.
it's even better.
I'll make something wrong, please. I made it.
Now
It is wonderful.
Now it's better. Yes.
It's not wonderful. You see only Zoom. Now, do you see the presentation?
Yes.
We do. It's fine. You can keep going.
Okay, okay. Please. Now it's okay, I think. So the Nobel Prize in Physics from 2022 has been awarded to Alain Aspect from France, John Clauser from United States, and Anton Zeilinger from Austria for their work in quantum theory. And as usual, the mass media called this event part of the second quantum revolution, and it includes quantum computing and other super technologies. Here, I'll discuss Alain Aspect version of Einstein-Podolsky-Rosen thought experiment. And I'll show that there exists a dependence, internal dependence of the simultaneous measurements but made by the two pairs of linear polarizers operated in each leg of this apparatus during this experiment. The corresponding Shannon-Kolmogorov information flow, or you can call it noise also, linking a polarizer from one leg to a polarizer from the other leg is proportional to the absolute value of this function of dependence. And it turns out that if Bell inequality is violated, then this information flow is strictly positive. Moreover, if you throw out the absolute value of this function of dependence, you get the so-called signed information flow. And if you know the signed information flow, you can get the probabilities of the four probabilities which are predicted by quantum theory, quantum mechanics. So this signed information flow just predicts the corresponding probabilities, like quantum mechanics. Now let's go further. I'll make, because more of the listeners are mathematicians, I'll make a brief review of quantum mechanics. I'm sorry for I have to apologize before physicists here. The first axiom of the quantum mechanics is the principle of superposition, and any physical system, electron, hydrogen atom, and so on, can be associated with a unitary space, H. I denote the inner product in this way, which is linear with respect to the second law and anti-linear with respect to the first law. And the corresponding norm furnishes H with the structure of a Hilbert space. Now, we will consider only finite dimensional unitary spaces, and even more, only two-dimensional. This is the unitary plane, where qubits live. The non-zero members of H are called state vectors or psi functions or wave functions, if they are normed, of the quantum system, and it is support also any array C, psi, when C is the set of the field of complex numbers, carries the whole information of the state of the system at a fixed moment of time. And we represent this array by a normalized vector, unit vector. Chronologically, the physicists began with the statement that if you have two psi functions or two wave functions, any linear combination of these two functions with complex coefficients is also a psi functions of this system, and it is encoded in the fact that the space H is a linear space. So axiom 2, this axiom on observables, any physical quantity of the system, energy, position, momentum, is represented by a self-adjoint or Hermitian linear operator A on H, which is called observable of this system, and its spectre, it consists of real numbers, of course. It consists of all possible values of the physical quantity. These are the eigenvalues, of course, of the observable. The corresponding eigenvectors are normalized psi functions, such that under the state, if you take one eigenvector psi, under the state of psi, the physical quantity assumes as value the eigenvalue lambda I with probability 1. We fix an orthonormal coordinate system consisting of eigenvectors. This can be done. And in terms of the coordinate system psi capital, we have that psi is a linear combination of the basis vectors, and the square of the square of the absolute value of the coefficients are the probabilities that after the measurements, the quantity gets the corresponding eigenvalue lambda. And formally we define this sample space, The outcomes are the eigenvectors. Here you see only their indices, and the corresponding probability assignment are the corresponding probabilities predicted by quantum mechanics. The sum is 1 because C is a normalized vector. And we consider this sequence of all eigenvalues of A, lambda 1 up to lambda n. And for any lambda in the spectrum, we denote by U lambda. This is a subset of 1, 2, up to n, consisting of all lambda I, such that lambda I is equal to this particular lambda. This is the inverse image via this via the sequence. And this linear operator here, this is the projection of H onto the eigenspace H lambda corresponding to lambda. And moreover, the probability of this event U lambda, this inverse image, it is event in this sample space, is the square of the norm of this projection taken at the initial state of the system C. And moreover, we obtain the spectral decomposition of this operator. This is this expression with the projections. And we also consider the operator A as a random variable A from the set of outcomes 1, 2, up to n on the sample space with this probability distribution. This is the probability distribution is given by these formulas. And moreover, we can write that the probability of this equality A, this random variable A, is equal to lambda. It is equal to the square of the norm of the projection, also to these two expressions. It is easy to get them. This pure linear algebra. And it is important, we identify the event U lambda. This is an event in a sample space with this equality is equal to lambda, and call it also event. Immediately after the measurement, the system, the state of the system is changed and becomes this C prime, which is the projection over its norm. And this phenomenon is called reduction of the wave packet or wave function collapse. And this commutation AB equals BA is equivalent to existence of an orthonormal basis C, capital of H, consisting of eigenvectors both of both A and B. And moreover, if you take the spectral decompositions of A and B, then this equality, the commutation is equivalent to the commutation of the corresponding projections. Under these two equivalent statements, we have these projections. These compositions are equal. The projection on U lambda composed with the projection on V mu. Mu are the eigen values of the operator B. Is equal to the projection onto the event U lambda intersected with V mu. This can be done immediately. And then this AB equals BA it has this spectral decomposition. So we can define the event A equals lambda and B equals mu by identifying it with this intersection. So in this way, A equals lambda and B equals mu is equal to B equals mu, A equals lambda. And now without any ambiguity, you can define the logical operation AND. This in the case of non-commuting operator is not possible. So after the performing those two measurements, commuting measurements, you get this, the state collapses to C second given by these two expressions, regardless of their order. So we now give a main definition. Two measurements are said to be simultaneous if the corresponding self-adjoint operators A and B commute. In case of non-commuting operators A and B, one observes the phenomenon of complementarity. This is a term introduced by Niels Bohr. In particular, you cannot define the logical operation AND. Moreover, in general, the collapse of the initial state depends on the order of the measurements A and B. So these two expressions are not equal in general. And now we form the expected value of the random variable A at the state C. It is defined in the usual way. This is the expected value of A at C is given by this expression. And we have this expression for expected value of A, this general expression for expected value of A. And then the standard deviation of the random variable A at state C is again defined by the usual formulas. And as a consequence of Cauchy-Bunyakovsky-Schwarz inequality, one has this inequality. The standard deviation of A times the standard deviation of B is greater or equal to this expression. It depends on the commutator of A and B. And in case this commutator is not zero, in general, the standard deviations of those two random variables cannot be simultaneously small. And this is known as Heisenberg uncertainty principle. The physicists say that the physical quantities, which corresponds to A and B, at this state C have no simultaneous reality. Now, axiom 3, composite systems. If a physical system with state H, space H, can be decomposed in two subsystems 1 and 2 with those corresponding state spaces H1 and H2, then H is their tensor product. In state C, this is an important definition. A state C is said to be separable. Sometimes they say product state. If there exist states C1 and C2 in H1 and H2, such that C is their tensor product. Otherwise, C is called entangled state. In the case of product state, we can, given C, you can, the corresponding C1 and C2 are unique up to a phase vector. So you can then, if you know the wave function of the composite system, you can recover the wave functions of the subsystems. But in the case of entangled state, this is not possible because in this expression of C as a sum of products, this expression is not unique. This expression is not unique. This is one of the reasons why entangled states play a key role in quantum information theory. And this special entangled state C, which is given by this formula, is called singlet state. C1 and C2 are basic vectors in the plane. Orthonormal basic vectors in the plane. Now, another axiom is so-called Schrödinger equation that describes the dynamic of the wave function during the time. This is a linear equation. I'll not discuss it here. And now I'll begin with the description of Einstein-Podolsky-Rosen paper. This paper, which is from 1935, it begins with specification of the meaning of some words. They defined those things, element of physical reality. It exists if and only if it is determined by experiments and measurements. Complete theory means that any element of the physical reality, for any element of the physical reality, there exists a corresponding non-contradictory mathematical counterpart in the theory. So this is complete theory. And reality of a physical quantity, this is important notion for this paper. If one can predict with certainty its value without disturbing the physical system, with the physical system, then the quantity has a counterpart in reality. Later, this thesis was called realism. In other words, the value of the quantity must exist before the measurements. Already exists as a counterpart in the physical reality before the measurement. And it is only revealed by the measurement. This is the philosophical part of the theory. The quantum mechanics is supposed to be a complete theory in physical, if its physical reality consists of quantum systems and with associated unitary spaces, spaces of states. They are furnished with Hermitian linear operators representing the measurements. By the way, I'd like to note that this is not a category because the composition of two Hermitian operators is not Hermitian. It is Hermitian if and only if they commute. So moreover, the wave functions are supposed to carry the whole information about the system at this state. In this case of non-commuting operator, you can see the phenomenon of complementarity. An example of such operators that do not commute are the operators of momentum and coordinate of a particle having a single degree of freedom. They do not commute. And this means the following: if psi is an eigenfunction of A corresponding to the eigenvalue lambda, that is, if A lambda is lambda psi, then the momentum has with certainty value lambda whenever the particle is in state psi. So the momentum has a counterpart in reality. This is the necessary and sufficient condition for some quantity to have a counterpart in reality. On the other hand, B psi at this state, eigenstate of A, is not proportional to psi, so the coordinate has not counterpart in reality at this state psi. If we apply the measurement B in order to get the value of the coordinate, then the eigenfunction psi of A collapses into an eigenfunction of B, which in general is not an eigenfunction of A. And now the momentum has no counterpart in reality. The usual conclusion of physicists in this case is that when the momentum is known, the coordinate has no physical reality. It is also said that the momentum and the coordinate have no simultaneous reality. In now description of Einstein-Podolsky-Rosen experiment, it considers a composite system with two subsystems 1 and 2, two particles. We interact from some time from t0 to t equal t capital, and after which time they do not there is no longer any interaction between the two particles. So we suppose that we know the states of the both parts before the interaction, and then Schrödinger equation will give you the behavior of the wave function during the time, and it is calculated for any t which is greater than 0. Including all those momentum that in which there is no interaction. So because of the entanglement, using C1 cannot calculate the state in which either one of the system is left after an interaction. This was the remark about separable or product states. In such a state, you can calculate the state of each one, either one. The only way this can be done is to apply further measurements. And when you apply the operator A1 of momentum at the first particle, and psi collapses to this tensor product UP with phi p, when UP is an eigenfunction of A1 corresponding to some eigenvalue, and phi p is an eigenfunction of the operator A2 of momentum of the second particle. So in particular, the wave function phi p fixes the reality of the second particle. If you apply the operator BF coordinate, B1 of the coordinate, we get the same phenomenon. It collapses to Vx times Cx, when Vx is an eigenfunction of B 1 and Px is an eigenfunction. Px is an eigenfunction of the operator B2 of the coordinate of the second particle. So the operators A and B, A2 and B2 do not commute. The momentum and the coordinate of the second particle have no simultaneous reality, which is a contradiction because after the interaction of the second particle has only one reality. And here you have the reality fixed of the second particle fixed by C of x, and the reality of the second particle fixed by phi p of x. And this is a contradiction because after the interaction, the second particle has just one reality. This is the conclusion of Einstein-Podolsky-Rosen. And here is the description of Alain Aspect version of Einstein-Podolsky-Rosen experiment. He considers two photons prepared in the singlet state. Here is the source of those photons, which move in opposite directions. And this is described here in the scheme of its experiment. And in 1964, the Irish physicist John Stuart Bell deduced under the assumptions of local causality and realism that if measurements are performed independently on the two separated particles of an entangled pair, then the assumption that the outcomes depend upon hidden variables. By the way, Einstein never used this term, hidden variables. The outcomes depend upon hidden variables within each half implies a mathematical constraint on how the outcomes on the two measurements are correlated. This constraint is named Bell inequality. Bell then showed that the quantum physics predict correlations that violate this inequality. Hence, the only way that the hidden variable could explain the predictions of the quantum physics is that if they are either non-local, which is to say that somehow the two particles are able to influence one another, no matter how widely they have been ever become separated, or non-realistic, that is, the values of the quantities do not exist before the experiment and are revealed by the experiment. An important condition under which Bell inequality is true is that the measurement at the one leg of the apparatus does not affect, that is, it is independent of the measurements of the other leg. Alain Aspect witty considers pairs of linear polarizers operated in each leg of the apparatus. Each pair has a time switch, which interchanges the polarizers, the corresponding time being shorter than the time necessary for a light signal to travel from one of the pairs of the polarizers to the other. So now the Einstein locality assumptions for independence is satisfied in this way in his experiment. Below, we show that if Bell inequality is violated, then the total information flow linking a polarizer from one leg to a polarizer from the other leg is strictly positive. That is, in this case, the experiments performed on both legs are informationally dependent. And now I'll go back to my work on dependence of two events in a probability space. I had a report in that in that seminar, but I'll repeat here some important parts of this report. Any pair of A, B of events in a probability space with probabilities alpha and beta, respectively, produces a Kolmogorov, in Kolmogorov terminology, a partition of the corresponding sample space. This is the partition. So you have this event A, in fact, produces a binomial experiment, A united with AC. B produces another binomial experiment, B and BC. And we consider the joint experiment of both binomial experiment. It is this experiment, which is written here. And the corresponding probabilities and the probability distribution, the corresponding probability distribution, this is distribution because the probabilities sum to 1. They satisfy this linear system, and then solving this linear system, you get these solutions that depend on one parameter. I choose the parameter to be theta equals C1. C1 was the probability of the intersection of A and B. And this is a line in the corresponding space, a linear space with coordinates C1 up to C4. And this constraint condition that C, K are probabilities between 0 and 1, they are equivalent of this property. Theta, this C1 theta, belongs to a closed interval that depends on alpha beta with the left endpoint maximum of 0 and alpha plus beta minus 1, and the right endpoint minimum of alpha and beta. Sorry. After that, we form the Boltzmann-Shannon entropy of the probability distribution C1 up to C4. It depends on theta. And this is the entropy function. This is the entropy function. This entropy function has has a very nice behavior. It is a function in theta, strictly increases on the interval from the left endpoint to alpha beta. Alpha beta is a member of the interval, this product, and strictly decreases on this interval alpha beta to the right endpoint, in thus having a global maximum at theta equals alpha beta. This is called entropy function, and its value is called entropy of the events A and B. And we modify this function, but before that, I'd like to make another remark concerning a very simple theorem in a sample space with equally likely outcomes. If theta is equal to alpha beta, then the events A and B are independent. If theta coincides with the left endpoint of the interval, then one of the events is a subset of the other, so the complement of the other. If theta coincides with the right endpoint, then one of the events is a subset of the other. So you have, in this case, strict negative dependence, and here strict positive dependence. And when theta is alpha beta, then they are independent. And comparing this theorem together with the behavior of the entropy function, this motivates us to use the entropy as a degree of dependence of the events A and B. And we normalize this entropy function and obtain a continuous function E alpha beta from this defined on this compact interval onto the interval -1, 1. It is defined in this way, and its behavior is similar to the regression coefficient in probability theory. And the value of the function at some theta is said to be degree of dependence of the events A and B. Then this function strictly increases on the whole interval from -1 to 1 with it is 0 exactly when the entropy has its maximum. So the events A and B are called negatively dependent if theta is to the left of alpha beta, and positively dependent if they are to the right of alpha beta. And when theta is alpha beta, the events A and B are independent. In this case, the entropy is maximal. It corresponds to our intuition that the two events are independent. The entropy is maximal. There are no relations. Now, we repeat the definition of a joint experiment used by Kolmogorov and also by Shannon of two binary experiments, A Gothic A and AC, and B Gothic B and BC, with those probabilities. And they define the average quantity of information of one of the experiments, A Gothic and B Gothic, relative to the other. It is defined by this formula here. This formula here. This is what we call information flow. And in this particular case, we have that this information at theta is equal to this difference, the maximum of the entropy function at alpha beta minus its value at theta. So, because these two expressions are the maximum in the corresponding subintervals, then you get that our dependence function is expressed via the information flow using these formulas. And from these formulas, it turns out that the degree of dependence of two events does not depend on the choice of unit of information. And now I'll introduce some notation. H means unitary plane with this inner product. This is the identity linear operator on H, and this is the tensor square of H, with furnished with the natural inner product given by this formula, and by U2 we denote the unit sphere in this tensor product. The specter of A is just the real specter of this Hermitian operator A with trace 0. It has this form when lambda 1 plus lambda 2 A this sum is equal to 0. This means trace 0. And the corresponding eigenvectors form an orthonormal frame. This is an orthonormal frame formed by the corresponding eigenvectors of A. And by HAA, we denote the eigenspaces, corresponding eigenspaces of A. And now let's introduce some notation. That follows is a pure linear algebra, in fact. We fix an orthonormal frame, H, H1, H2 for H, and identify the self-adjoint operators with their matrices with respect to H. Here is the general matrix of such self-adjoint operator with eigenvalues 1 and -1. This is the form of it. And the corresponding eigenvectors have this form here. You can calculate them immediately from the matrices. And we denote by any nu in the interval 0p with b nu is equal to a nu. This is a copy of A acting on the other side of the tensor product. Moreover, those tensor products here form, and those tensor products here form orthonormal frames for the tensor square of H. This is just elementary linear algebra. And now we said that A script mu, this is A mu tensor with the identity operator on the second factor of the tensor product. And B nu, B script nu is the identity on the first factor of the tensor product multiplied by B nu. It is easy to check that both operators have the same eigenvalues -1, and the eigenspaces have these orthonormal frames. This is just elementary linear algebra. I'll not discuss it. So because in particular this U A mu and tensored with U B nu forms the orthonormal coordinate system of the tensor product, then those two operators A script mu and B script nu commutate because they have a common common eigenvectors. And we take a unit vector in the tensor product, and we denote by SC in this way the sample space with set of outcomes, this tensor product. This is the corresponding frame consisting of eigenvectors. And the corresponding probability assignment P1, P11, P12, P21, P22 is given by these formulas here. And with an abuse of the language, we consider the observable mu as a random variable on this, on the set of outcomes of this sample space. And I repeat everything which was said about the random variables A and B in the beginning of these lectures, but in terms of A script and B script. So we identify, moreover, because they commute, A mu and B mu script commute, you can define the intersection of those events, which is identified with this event in the sample space. And using this identification, you get that the probabilities of that A mu is a given, A mu, this random variable, has a given value lambda I, and probability of B nu has a given probability lambda j. They both equal to 1/2. This is because we are using the singlet state as an initial state. And moreover, the probabilities of those intersections are given by these formulas here. It's very simple probability assignment. Now, moreover, the random variable, the product of the random variables A mu B nu has this probability distribution given via these formulas. It assumes value 1 and -1. It assumes value 1 with probability sine square of this quantity, this angle, and -1 with cosine square of the same angle. And moreover, for lambda, which are different from those 1 and -1, this is 0, of course. The expected value of this random variable is minus cosine of mu minus nu. And I want to go here to the initial, to the notation used in my work on dependence in a probability space. So for simplicity, I denote by A, this A mu equals lambda 1 A mu, B nu equals lambda 1 B nu. So AC is A mu equals lambda 2, and BC is B nu equals lambda 2. Alpha and beta are 1/2. This pair of events in the sample space with half probability, with probability 0.5, produces an experiment, joint experiment, and the probabilities of its result in this case are given by those formulas here. Once again, I repeat that this is a simple linear algebra. Anybody can do that, those calculations. The entropy of the probability distribution is given by this formula, in this particular case by this formula here. And the function Et can be extended as a continuous on the interval, the closed interval 0, 1/2. In particular, the maximum of that function, entropy function, is at 1/4. This is alpha times beta. 1/4, this is 2 logarithm of 2. This natural logarithm. And the minimums of the both subintervals are equal to logarithm of 2, then the total minimum of the function at the interval 0, 1/2 is logarithm of 2. Taking into account these values, the values of the extreme of entropy function, we obtain this formula that relates E theta, the dependence function E theta, and the entropy function. And so it turns out that if the events A and B are independent, exactly when the entropy is maximal, equal to 2 logarithm of 2, when, or equivalently when E theta is 0. In case E theta equals -1, in E theta 1, the entropy is minimal and it is equal to logarithm of 2. In this context of bipartite quantum system that describes aspect version, optical version of the experiment of Einstein-Podolsky-Rosen, we considered the pairs of linear polarizers operated in each leg of the apparatus as pairs of cell-adjoint linear operators, A mu I and B nu J, where mu I and mu J are the angles of the polarizers. Note that each pair has a time switch which interchanges. I discussed this. Each pair of operators acts on the state space of the corresponding quantum subsystem, a unitary plane. So by tensoring, you get the unitary space of bipartite quantum system. And we obtain those operators A script and B script with spectre 1 - 1 on the state space of the tensor squared of the whole quantum system. Moreover, for each I and J equals 1 and 2, the operators A mu I and B mu J commute. And now we apply the previous considerations about those commuting operators and get the average quantity of information of one of the experiments A Gothic mu, A Gothic mu and B Gothic mu relative to the other is defined by this, in particular by this formula. And the definition of the degree function yields immediately that the information flow at theta is the absolute value of E theta times logarithm of 2 for any theta in the interval 0, 1/2. Translating into the language of information theory, you have that E theta is -1, it's minimum, if and only if the information is the maximum of this information flow, this logarithm of 2, and E theta is equal to 0 if and only if the corresponding information flow is equal to 0. And under the condition, this condition, the experiments A Gothic mu and B Gothic mu are said to be informationally independent when the information flow is 0. Otherwise, they are called dependent. So we now modify slightly the information flow and form this quantity, signed information flow by these formulas. Here, simply we throw out the sign of absolute value and get the average quantity of signed information of one of the events A script mu relative to the other B script mu. And in particular, the value of the signed information flow, because the function E is bijection of this interval I alpha beta to the interval -1, 1, it is a bijection. You are using its inverse, E inverse, and apply it on this signed information flow multiplied by 1 over logarithm of 2, and you get theta, this parameter that describes the whole all predictions of the quantum mechanics about the probabilities of those experiments, the 4 probabilities of those experiments. I'll show you these. Here are those probabilities. So the signed information flow predicts all of them, predicts the probabilities which are guaranteed by quantum mechanics. And here we have some functions, information flow, depending on two binary experiment, A Gothic and B Gothic. Given by these formulas, they represent the intensity of the information flow or signed information flow. And it's turned out that their ranges coincide with this interval, 0, 4 logarithm of 2 and minus 4 logarithm 2, 4 logarithm 2, respectively. And now Bell's inequality. This inequality, which is obvious, the product of, if you suppose that those random variables A script and B script have values before the measurement. So this is the assumption of realism. So we suppose that they have values +1 and -1, and this quantity has absolute value equals to 2. When you apply the probability theory, you get that the expected values of those products, absolute value of this expression is less or equal to 2. So we denote by B mu1, mu2, mu1, mu2, this function, which is under the sign of absolute value. And this is cosine of mu1 minus mu1 plus cosine mu1 minus mu2, and so on. This is so-called Bell function. I called it Bell function. He proves that if there exist additional variables which restore the quantum to the quantum theory, causality and locality, then the above inequality is satisfied. The equality information flow is equal to 0 is equivalent to the fact that all those differences are 90 degrees, mu I minus mu j. All those 4 differences are 90 degrees. And in this case, the Bell function is 0. The Bell function is 0. So if, in particular, the Bell inequalities is violated, then the total information flow A B is strictly positive. So this means, in other words, that the experiments A and B are informationally dependent. And here we have examples which are calculated using the Java program, which is made by my friend Dimitar Gelev. It is published in on this link here. This link, if you click this link, you'll get the corresponding program. And here, I'd like to give you in the aspect Alain Aspect experiment, the corresponding angles. They are p/8, mu2 is 3p/8, mu1 is p/4, mu2 is 0. Then we obtain that B, the value of B, the Bell function B, is 2.388 and so on. So it is bigger than 2. It is violated. The Bell inequality is violated. The information flow is 0.16-15415. And the signed information flow is given by this number here. And here are considered other examples. I'll not consider them. You can see them in my presentation. Will be published in the site of our section, linear algebra and logic. So here is the description of the program of Mitko Gelev. The description also is contained in the corresponding link. And this is acknowledgement of the work of perfect work of Mitko. the numerical examples are invaluable for my work. And I also to express my gratitude to the administration of the Institute of Mathematics and Informatics for creating perfect and safe conditions of work. And this is here is the last sentence in the Einstein-Podolsky-Rosen paper. You can never see hidden variable here. So, moreover, I'd like to make a remark about my future work. During the mid-50s of the last century, the frontman of French psychoanalysis, this is Jacques Lacan. Jacques Lacan, he stated his thesis that the woman doesn't exist. Psychoanalytically, she doesn't exist. I'd like to state my thesis here, that the noiseless quantum computer doesn't exist. So thank you very much.
Let's thank the speaker very much for his talk. If you have any questions, you simply can ask without asking for permission.
Thank you very much for the presentation.
You're welcome, Vanya.
When you speak about Hermitian operators,
They are identical to self-adjoint operators.
That's what I wanted to ask. That it is for you, it is the same as self-adjoint. Okay.
Yes.
Thank you.
Some other questions or comments?
Wishing you luck in your future endeavors, Vanya.
Sorry, I cannot hear, Vanya, please.
Wishing you success in your future work.
Thank you. So I hope you have read the last sentence of Einstein-Podolsky-Rosen paper, and moreover, I cite here one of the Nobel laureates, Anton Zeilinger. He says in one of his work that it is operationally impossible to separate reality and information.
Interesting.
Well, this all. If you have question, please.
Okay, if no questions, just thank the speaker once again. We don't know where is the next talk, but when we have the speaker, we shall announce this in time.